Alrighty, guys, welcome back. We are wrapping up the semester here with Chapter 11. This is the third edition, Chapter 11. Now, it seems like probably this might be a little intimidating that we're starting a new chapter in the final week, but in fact, this is not really a new chapter. This chapter more like cements everything that we've learned about syntheses from the previous chapters and kind of brings it all together in one space so that it kind of helps you um, bring everything together. I guess I want to say synthesize the whole synthesis knowledge that you have for organic chemistry. So that's what we're going to do. We have two lectures on that, just a small lecture on green chemistry as well, not like an important one. But again, what we're doing here is we're just kind of helping you process all the syntheses that you've learned from previous chapters and kind of get them in order before you take the final exam. So don't worry about new material. This is basically just a direct review for the final exam. So think of it that way. Okay, so starting with what we know, this lecture is going to cover basically one-step syntheses and like how you can kind of identify the reagents that you need, which is something that we've done before on our exams. And then the next lecture, we'll talk about multi-step syntheses, and in particular, what we call retrosynthetic analysis as kind of a method for solving those problems. So yeah, so again, I've asked you to do this before on the test, so this isn't going to be a big surprise here. If you have a synthesis problem where you have the reactants and the products, then it's up to you to figure out, what changed from the reactants to the products. This is clearly the addition of a bromine uh, on two separate carbons across a double bond. So in order to do that, we would need the halogenation compound, or Br2 in this case. So now in order for us to move forward, we need to make sure that we understand all of the reactions, the reagents, and all the other solvent requirements as well before we're ready to tackle the multi-step synthesis problems. So this is a good time to kind of pause the video, read through chapter 11 just at the beginning. This is going to give you kind of a philosophical background for these syntheses problems, and then work through conceptual checkpoints 11.1 and 11.2. That's the third edition textbook. If you have the second edition textbook, that's 12.1 and 12.2. So just keep that in mind. Okay, so moving on, thinking in terms of one-step synthesis, let's build it up into a two-step synthesis. Remember that we have had two-step synthesis strategies explained to us before when we talked about elimination and addition reactions. So for example, we know that we can move a functional group or move a pi bond um, using different sequences of elimination and addition. So like in this case, if we have an alkyl halide and we want to get to the more substituted alkyl halide. In order to do that, our intermediate is going to be a pi bond. So in order to form this pi bond, we know that we need to do an elimination reaction that eliminates this bromide, and it provides us with the more substituted alkene rather than the less substituted alkene, which would be, coming down here. So to get the Zaitsev product, that means we have to use a strong, small base, and so a non-bulky base. And then once we have that, now all of a sudden we know, we just need the Markovnikov addition of bromine across the double bond. So we just need HBr. So it's just a two-step process. We use sodium ethoxide to get to our alkene, and then HBr to get to our alkyl halide. So that's kind of the way that it moves. Now, that's not the only thing that we could do. For example, like we could do an elimination reaction where we use a bulky base. In that case, we'd get the Hoffman product, which is here. Then if we use HBr and if we just use HBr, that gets us back to where we were. But we could use HBr in the presence of peroxides. That would give us the anti-Markovnikov addition of the bromine, and that would give us this product here. So it's kind of like as we do each step, we're spreading out almost like a spider web. Like we know we can go from here to here. Oftentimes we'll double back, and we can double back by a different route than the one that we took. But these are all things that we need to weigh as we do these multi-step synthesis problems. Okay, so if we had instead an alcohol, alcohols have a similar set of steps. Basically, though, instead of being eliminated directly, you know that you have to protect the alcohol or turn it into a sulfonate. So we use tosyl chloride, for example, tosyl chloride in pyridine. That gives you a good leaving group, which then you can do an elimination reaction on. So if you do the elimination reaction, that gives you the Zaitsev alkene here. Or if you did the bulky base down here, that would give you the Hofmann product down here. Now we know that we can also take an alkene and turn it into an alcohol using one of our hydration methods. In this case, we have hydroboration here. Remember, that's the anti-Markovnikov addition of H and OH. And then we have oxymercuration, demercuration here. That is the Markovnikov addition of H and OH. And then finally, if we have this product here, so we want to get, let's say we want to get to the more substituted alcohol, all we need to do is acid catalyzed hydration. So we could just put H3O plus here. That gives us the Markovnikov product. Now, that can be messy sometimes. In this case, it's not a problem. So you could just do H3O plus, it's no problem. Remember that if you need the Markovnikov addition of an alcohol across a double bond, use the oxymercuration, demercuration method down here. That will always work and you won't have to deal with rearrangements. Okay, so that's a few things that we've learned already. We also know we can move a pi bond using a sequence of addition and then elimination. So almost the opposite of what we were just doing there. So starting from this pi bond, let's say we want to move it to this pi bond. Well, the first step is we do an addition reaction and we get the bromine on the carbon that's going to be in the middle of those two pi bonds. Like this is a vinyl carbon in the reactants and it's a vinyl carbon in the products. That's going to be our key step. To get the bromine on this one, all we need to do is have the Markovnikov addition of the bromine. So we just use HBr again, and that gives us this tertiary alkyl halide. To do the next elimination, this time we want the Hofmann product. If we use a small bulky base, we would just get back to our original reactant. So we need to use a big bulky base like potassium terbutoxide, for example. So we just do an addition of HBr and then elimination using a bulky base. So you can kind of follow along. Again, this is exactly what I just said here. You use HBr to do the Markovnikov addition and then a big bulky base like potassium terbutoxide to get the Hofmann alkene. You could also, of course, you can do a if you instead use HBr in the presence of peroxides, that gives you the anti-Markovnikov bromide, alkyl bromide, and then use a bulky base down here. Well, the bulky base would give you the Hofmann product, which would be this product here. So yeah, now this might seem easy as I say it, but of course, the reason that I can say these things so quickly and easily is because I've had a lot of practice with them. So make sure that you're able to remember the reagent conditions, or at least you have, a reference notes. Obviously, you're taking your exams at home, so if you have your reference notes that you can look at very briefly and remember what you know about the reactions, then that's gonna get you pretty far on this stuff. Okay. Now, alkanes to alkenes. We can also do that. We learned about the halogenation reactions, the radical halogenation reactions, back in chapter 10 or chapter 11, depending on which edition you're using here. If you have, like in this case, methyl cyclohexane, you do a radical bromination, your primary product is going to be the one that it has the bromine on the most substituted carbon. So you can predict pretty well that you're going to get the bromination on this position here. You can also use like allylic bromination if that's necessary. Remember, that's the NBS. That's the NBS reaction. Now, once you're here, you can do an elimination reaction. And you can either, in this case, use a bulky base. That would give you a product similar to what we saw on the last problem. Or you use a small, strong base, and that gives you the Zaitsev product, which is what we see here. Now, what's interesting is once we have a double bond, we can actually get it to a single bond again. Like we can take it back, using hydrogenation reactions, go to hydrogen and platinum. Or if you want to get it to a triple bond, and this doesn't work in this case because this is on a ring, right? We can't get a triple bond onto this ring. But what you can do is you can halogenate the alkene That gives you two neighboring bromines. So they're vicinal bromines. And then you can do a double elimination reaction using excess NH2, sodium amide. That's what we covered in the last chapter. So basically, you can take this double bond, turn it into a triple bond. So now I hope you kind of understand, like, as we see, you know, this is how you can make an alkyl halide. Alkyl halides can turn into alkenes. Alkenes can turn back into alkyl halides, or they can turn into alkynes. Hope you can see that this is just like spider webbing out as we like integrate it into more and more reactions that we know. Okay, now here's the big one, and this is going to start the next chapter or the next section as well. So this is just a brief discussion. Sometimes it may be necessary that we add carbons or we remove carbons from a molecule. And this is going to be a big hint for you in Organic Chemistry 1. So this is going to work in Organic Chemistry 1. Basically, there's one reaction that we've learned that removes carbons from the skeleton, and then there's one reaction that we've learned that adds carbons to the skeleton. So simply by keeping track of like how many carbons are in your molecule, you can know, oh, I need to add carbons on. Well, this is the way that we add carbons on. Oh, we need to remove carbons. This is the way that we remove carbons. So just keep that in mind. Basically, I'll just say what it is right now, and we'll talk about it more in depth in the next video. To remove carbons, you're going to need to use ozonolysis. To add carbons, you're going to need to use alkylation of a terminal alkyne. So just kind of keep that in mind. So this is exactly what I was just saying. There's only one transformation that increases the number of carbons in a molecule. That's the alkylation of a terminal alkyne. So what you do is you take your alkyne and you deprotonate it using sodium amide. That gives you this nucleophilic carbon. And then you just do a substitution reaction, SN2 substitution reaction. In this case, we use like a propyl bromide. So SN2, no trick here. Got our nucleophilic attack, loss of a leaving group, and that gives us our new primary chain here with 7 carbon atoms. So we went from 4, we added 3, now we have 7 carbon atoms. So that's going to be an easy way to figure out what reaction you need to do moving forward. And then, yeah, as I mentioned, there's only one way that we've learned to decrease the number of carbons in a molecule, which is ozonolysis. So if you take an alkene and you ozonolyze it, you basically you start with 5 carbon atoms, you end up with 4 carbon atoms. Next semester, you'll learn a set of reactions that will, stuff that you can do with these aldehydes and carboxylic acids. And also next semester, we're going to learn a lot more ways to build up carbon skeletons. But for this semester and for the final exam, there's only these 2 ways. So that's going to be a big hint. And we'll talk about what that means in the next lecture. So, okay, I hope that made sense. And I hope you can kind of see how this is going to work out. In the next lecture video, we're going to talk about what's called retrosynthetic analysis, which is a really a simplified way to get from the reactants that you're given to the products that you're given in a multi-step synthesis problem. So we'll give that a try, and I will talk to you soon.